And finally, we are now going to see the fourth part of the second exercise, which starts with a definition of a primitive polynomial. Let f be this polynomial. As usual, you already know, you have seen it in the other parts, where the coefficients are the ai's and they are coming from this ring capital A. This is called primitive if the ideal generated by the coefficients is this ideal generated by the identity element, which you already know is the entire ring A. If this happens, then we call f a primitive polynomial, or just simply call it primitive. Now this is what we have to prove. Prove that if f and g are two elements in Ax, then their product fg is primitive if and only if f and g are both primitive. Because we already have f with us, and let's just assume that itself as the entire f, that is, which has the coefficients ai. We consider g also, because we have two polynomials f and g. Let g be this b0 plus b1x and so on plus bmx to the power m. So the coefficients of g are these bj's. And then what we do, we consider b, which is the ideal generated by a set C, where this is C. The elements in C look like this. They are sums of products like this ai bj, where I plus j is equal to k. Once you choose this k from this range between 0 and n plus m, then you get one sum. And what are I and j? I and j are the suffixes that you can vary. Say you will vary I from 0 to n, because the coefficients of the polynomial f are a0, a1, a2 up to an. So I goes from 0 to n. Just like that, j goes from 0 to m, because the coefficients of g are these bj's. Keeping this thing intact, that is I plus j equal to k, because you have already chosen k, all possible I and j have to be considered, and accordingly you will get these products and their sum is being taken. That is one element of this set C. Just like that, you have other elements for the other choices of k. For any such k, you are getting one such element. And this set C, of course, you can understand that it's a finite set. But anyway, the point here is that it's a subset of our ring A, because after all these coefficients are coming from A. So these elements ultimately are inside the ring A, and that is why C is a subset of A and B is the ideal generated by C. What does that mean? It means that B is the smallest ideal of the ring A that contains C as a subset inside of it. Alright, now what are we going to do with it? So this is one half of the proof, where we assume that Fg is primitive. Let Fg, the product, be primitive. Then by definition of primitivity, this ideal B is the entire ring A, or the ideal generated by the identity element. Why? Because you recall the definition of primitivity. A polynomial is said to be primitive if the ideal generated by its coefficients is the entire ring. Look carefully and see that these are actually the coefficients of the product Fg, and B is just the ideal generated by the coefficients of Fg. So assuming that Fg is primitive just means this. Alright, so that is one thing that we are getting just straight from this assumption. And next we note these things as well. The ideal generated by the coefficients of f contains B inside of it. How? Well, what type of elements do you have in this ideal, they are sums of products of these AIs, finitely many of them, of course, anyway there are finitely many, products of AI by ring elements coming from our ring A. So, a typical element in this ideal will look like this, say something alpha times A0 plus beta times A1 and so on, where alpha and beta they are coming from our underlying ring A. Just like that, a typical element of B, because B is the ideal generated by these elements, a typical element of B will also be a sum like that, where what will you do? You will take finitely many elements like this, which themselves are sums, multiply them by ring elements, and then take the sum of such products. Okay. And in doing so, say you just take one element which looks like this for some k. You multiply that by some ring element, say R. Then by distributive law, R goes inside and gets multiplied with each term of this sum. And then that product, just that product, this element times a ring element R becomes what? A sum where each term in the sum is a multiple of AI by a ring element. By which ring element? R times Bj. And then when you add finitely many such products, ultimately it again becomes a sum of multiples of AI, which is how the elements in this ideal look like. And that is why any element in B is also here. And similarly, any element in B also is a sum of multiples of Bj's, but that's how elements in this ideal look. So that is why B is also contained in this. However, our assumption tells us that B is the entire ring. So the entire ring is contained in this ideal as well as this ideal. But these are, by definition, since they are ideals in A, themselves are contained inside the ring. So both of them must be equal to the entire ring. And that is why, by definition of primitivity, because this is equal to 1, so the polynomial f is primitive, and because this is equal to 1, g is also primitive. So we have proved that if fg is primitive, then f and g are both primitive. And now we have to prove the converse. So conversely, let f and g be primitive, and now our aim is to prove that fg is primitive. Contrary to that, suppose fg is not primitive. What does that mean? It means that the ideal generated by the coefficients of fg, which is our b, is not the entire ring. Alright. Now because this is not the entire ring, you go back to the statement of corollary 1,4. Any proper ideal, this now has become a proper ideal because of this supposition, is contained inside a maximal ideal. That's what corollary 1,4 says. So this B will also be contained inside a maximal ideal of A. Let that maximal ideal be M. M is a maximal ideal of A which contains B inside of it. M may be equal to B, but M being a maximal ideal is itself a proper ideal. You keep that also in mind. Alright, next. Now consider the ring Kx, the polynomial ring, where K is this quotient ring of our ring A by the ideal M. Because M is maximal, you know this well-known result that K is a field. Alright, any quotient of a ring by a maximal ideal is a field. And because K is a field, this Kx is an integral domain. The justification you can find in the second corollary to lemma 391 from Herstein's topics in algebra. In spite of the slight difference between the definition of integral domain here in this book and in Herstein, it still works. Okay, you go through the small changes and see that it really works. The point now is that Kx is an integral domain, and K is this quotient ring, and that's why it's a field. Note also that the elements in K are the cosets of the ideal M by elements of A. Alright, what are we now going to do with this? Now we are going to do a calculation in this ring Kx. We start with M. It may be a little confusing at first, but do not get confused. Note that M is the zero element of K, of the field K. The field K is basically a quotient ring, right? So that's why I said just now that the elements in K are cosets of M by elements of the ring A. I emphasized that fact because of this. You do not think of M as the maximal ideal M anymore. M is the zero element of K, and hence automatically the zero element in this polynomial ring as well. But you can write this as this polynomial then, where the terms look like this: mx to the power k, where k varies from 0 to n plus m. Why we are suddenly considering this, it will become clear. But is it not okay to write that this is equal to this? Yes, actually that is okay. That is because you look at this polynomial, in it every coefficient is m and considered as a polynomial in Kx, every coefficient then is 0. That is why it is equal to 0. Alright. Now next we write this as well, where we haven't really changed anything except that in place of m we are suddenly writing this plus m. First of all, what is the meaning of this thing inside the square brackets? It is a general element. General element means it's just an element in where? In K. Why? Because it's a coset of the ideal M. This is how elements in K look like. Alright, but what is going on? Can we just suddenly replace M with this? Actually we can, but why? Is it equal to M? Yes, it is equal to M. But that is possible only when these sums are inside M. Are they inside M? Yes, they are inside M. But by what? How do we justify that these sums are inside M? Do not forget that M not only is a maximal ideal, but M contains our B also, that ideal. And the ideal B is itself is generated by elements like this. So in particular, these elements are inside B, and as a result they are inside M also. That's why this coset is just M. Okay. And then it continues. Then in the next line, we write in place of this coefficient, this entire thing, this. Actually, I have skipped one step. Note carefully that I haven't used brackets here, which indicates the fact that we are looking at a single coset of M, where the representative element is this entire sum, that plus n. But then the step that I did not write involves writing, providing brackets here, which would indicate that we are looking at a sum of some cosets of M, where the typical coset is aibj plus M. And you can do that because that is just how the definition of addition is in the field K or in the quotient ring A/M. And then once you write that, after that you naturally write this, because then you are looking at cosets which individually look like this, aibj plus M. By the definition of multiplication in K, aibj plus M is ai plus M times bj plus M. Alright. Now you look at this entire thing. It's a polynomial, right? Where the coefficients are these terms within the square brackets. And if you look carefully, it is the product of these two polynomials, because it has precisely the form that it needs to have to be a product of two polynomials. One of them is this, where the coefficient of the ith term is the coset ai plus m as I goes from 0 to n, and the other one is this, where the coefficient of the jth term is bj plus m, where j goes from 0 to m. I mean, you can see it for yourself. When you multiply two such polynomials, you introduce a new index k, and then you, after doing multiplication, you gather like terms, that is, you gather those powers of x where the exponent is same. That is why for a given k, we consider those I and j such that I plus j is equal to k, and then you write x to the power k. So after you gather those terms, the coefficients get added, and that's how you get one coefficient for a given k. And as k varies from 0 to n plus m, that's how you get the entire product. And now what have you got here? You have got the fact that the product of two polynomials in kx is equal to 0. And just now we wrote that kx is an integral domain. So at least one of them has to then be 0. So this means that we have written the reason also. Since kx is an integral domain, either this is equal to 0, 0 here means m, okay. Actually, even if you write 0, that's not a problem, but you have to interpret it as m, because that's the 0 element, or this is 0. So what does that imply? It implies that either all the coefficients of this polynomial are equal to m, that is, all ai plus m is equal to m for all such I, or all bj plus m is equal to m, all of them are equal to m for all such j. That is, either ai belongs to m for all these i's, or the bj's are all inside m for all the possible j's. This, however, is a problem, and this is the problem. If all the ai's are inside m, then obviously the ideal they generate would be contained in m, whereas similarly if all the bj's are inside m, then the ideal they generate would be contained in m. Now what was our hypothesis in this converse part? That f and g are both primitive. So what does that mean? It means that this ideal and this ideal are both equal to the entire ring, but then the entire ring is contained in m, which cannot be true, because if this is true, then m becomes equal to the entire ring, but that contradicts the maximality of m, because m by definition of maximality is a proper ideal, it cannot be the entire ring. So now we have no option, we just have to declare that our supposition is wrong. What was our supposition? That fg is not primitive, and that is why fg has to be primitive. So this completes the solution of exercise 2 actually entirely.